Welcome back to KTAL LP FM in Las Cruces, New Mexico, 101.5. We're talking about what makes a planet habitable. We did two sections earlier reviewing an earlier show about getting the temperature right and getting the right chemical elements on our planet and so on. Previous segment here, we talked about what the sun has to be like, and also on the planetary scale, we need land, we need the right size of planet, and we need an ozone layer, blah, blah. Now, we got into, at the very end recently, what life has to do. It has to capture radiant energy from the star, like our sun. That's because there was some, what we call available or free energy in the thermodynamic sense, in the mixture of chemicals in the early oceans. And when cells evolved, living cells, they started chewing that up, you might say degrading it, reducing the free energy content of the soup. That has to be replenished. So the critical thing was when some bacteria, some kin of cyanobacteria, evolved what's called photosystem 1. They were able to actually shift some electrons around, electron transport, and create energy-rich compounds, which is the basis of all life. If you look at us, we're pretty metabolizable ourselves. We do break down proteins and carbohydrates and fats, but we're just as much of an energy source. We embody a lot of what we call free energy. That had to be replenished. We're constantly degrading it. So the photosynthetic organisms are really supporting everybody else, and they would have to be doing that on any habitable planet. And then my wife, Dr. Llewellyn Kay, made an interesting comment that it was the evolution of photosystem 2 by the cyanobacteria, used to be called blue-green algae, that was critical for us, because then they could use water as an electron acceptor and we'd get oxygen. So that is free oxygen in the atmosphere. And there's a long story there about what happened when they did that. They, you might say, accidentally broke down the methane greenhouse that was really keeping us warm, and the Earth froze over substantially or perhaps completely. We sort of barely got out of it with bacteria being the continuation of life, and we got out of that thanks to volcanoes bringing in lots of carbon dioxide, which then kicked the temperature way up, and finally we equilibrated more toward normal conditions. So overall, I made just a short list. If you want to pick a planet that's habitable, you're an astrobiologist or an exoplanet studier, and you've got evidence from telescopic observations that there are planets surrounding stars, and it looks that they're at the right temperature and all that stuff. You want to pick a planet that was in a good neighborhood, that a supernova created enough of those heavier elements that we rely on. You name it, iron, iodine, manganese, carbon, oxygen. And then you want to look for one that's about the right size, near the size of Earth, for several reasons. It's not just comfort on gravity. It is retaining an atmosphere and, basically retaining an atmosphere. The planet also has to rotate nicely on a reasonable time schedule and pretty regularly at its distance from the star. Otherwise, you get pretty extreme temperatures. And you want the planet to be near a star that's along the main sequence, like our sun is, the type G stars. They're long-lived and not too hot. You also want to watch out for close neighbors, other planets that might chaotically disturb the orbit that your planet is in. And that can happen if you get a real crowd. Our orbit has been pretty stable for quite a while. Some of the planets have been knocked out. I'm trying to remember who said which of the outer planets actually got bounced out there by Jupiter. The other thing is you want to make sure that the planet has carbon and water in enough abundance, because there are very compelling arguments based on universal chemistry that says those are the elements that are going to support complicated molecules, therefore life. And then finally, don't expect that you're going to find more than one in a sample of, who knows, billions. So we're not likely to see one, and it's going to be pretty distant, almost for sure. Now, there are some details from a previous show that would be interesting to get into. So I've mentioned a number of times that the amount of energy put out by a hot body, well, almost any body, varies as the fourth power of the absolute temperature. Okay? So what's absolute temperature? That's measured from absolute zero. So I'm sitting in the studio, and John, what do you guess the temperature is in here in Celsius, Fahrenheit, whatever?
Here?
Yeah.
78.
78. Okay. Let's convert that to about 25, a little close, a little bit more than 25 Celsius. That's 298 Kelvin. That is above absolute zero. Now, what if we look at the sun? Well, let's round off our temperature to 300. The sun is at nearly 6,000, so that's 20 times higher in absolute temperature. But the amount of radiation it gives off is, again, proportional to the fourth power of that temperature. So 20 times 20 times 20 times 20, let's see, that's 400 times 400, it's 160,000 times more than us. So you get ramped up very quickly in energy with temperature. And figuring out that why that happens was a real triumph of physics around the turn of the 20th century. So there was a quandary called the ultraviolet catastrophe. With all the physics that was known up to around 1900, physicists said, okay, we know how many ways or modes there are for an object to radiate radiation. This is, the thermal radiation. And it looks like there's more and more as you go to higher and higher energy. And if they all have equal ability to be reached, then we should have more and more energy as you go to higher and higher energy of the particles of radiation. Okay, particles, that's what Max Planck realized. If you say that radiation comes in packets called photons that are quantized, then he worked out that you have a cutoff to the amount of radiation at these more energetic levels. And the relation that he got, if you take it mathematically, it integrates perfectly to this fourth power law for temperature. Sort of a spin-off of the whole thing, a really big spin-off of the radiation laws is you can explain lasers and masers, the light amplification by stimulated emission of radiation. And that's a natural consequence of these laws. It wasn't actually put to use, although first it was with microwaves instead of light. That's what the maser is. And think how many lasers are involved in our lives these days. Another thing that came up was the assumption that we know how far these exoplanets and other stellar systems are away from their stars. But you can even get back to, how do we know how far we are away from our sun? Well, let's just take a basic example, not trying to look by the sun, but let's look at a star that's fairly close compared to all the billions and trillions of stars that are out there. So let me get this ready for John there. Okay. So here we are on the Earth. I've drawn a picture of the Earth, and there's two observers. Could be the same observer at different seasons or whatever. Just looking across the diameter of the Earth, you've got observers at different view angles of this close-up star or its planet. So they see them against slightly different backgrounds of the distant stars. So there's an angle, the angle of parallax. So if you know that and you know how far apart you are in observations across the diameter of the Earth, you can say, now I know how far we are away from that interesting star that's close by. Now, you can get more extreme. Instead of just observing on opposite sides of the Earth, you can get on opposite sides of our orbit around the sun, and then you get an even bigger range of distances that you can examine. I'm trying to think how far it takes us. 30 light years or something like that. After that, it's hard to get telescopes to discriminate those tiny little shifts in angle. So what do you do after you can't use parallax? Well, actually it's sort of similar. You can try to image the star directly. You run up against the same limitation that telescopes can't tell angular sizes and angular offsets, very tiny offsets. Okay, I'm trying to think. Only 2 or 3 stars have actually had their sizes measured by the size of their image in a telescope. So what's another way? This worked for 124 stars so far. It's what's called lunar occultation. Occultation just means blocking. So you get the moon crossing the pattern of the stars out there, and of course it's going to eventually cover a given star, but not immediately. It depends on the angular size of that star. So it's a moderately slow process. A good telescope can see as the light diminish fairly quickly, but over a measurable time as the moon passes in front of it. Obviously, you have to have the dark limb of the moon to do that. And another way to get the distance to a star is with what's called eclipsing binary stars. So, oops, that's not that one. Okay. Most stars, I think, or at least half, are actually binaries, pairs of stars. We're pretty unusual. It would be pretty upsetting for our planetary orbits and our energy balance if we did have another sun out there. But a lot of stars do have a companion. So when they're separated from each other in angle, we see the brightness of both stars. But what happens when one star passes in front of the other? We block off part or all of the light from that other star. Okay, how does that help us? Well, if we know how fast the star is moving, then we can figure out its orbital separation